Welcome. This course is an kind of extension to the earlier course that was on integrated circuits, op amps, MOSFETs and their applications. So, in that course particularly what we have seen is basics of op amps, basics of MOSFET, and we also covered the fabrication part, how we can fabricate an integrated circuit. To be precise, we understood how to fabricate a MOSFET. Now, once we have a basic idea of all these modules and all these applications, we need to move further and understand its practical applications, how to design, how to simulate and how to implement the things that we have learned. So, in this particular course our focus would be on op amp practical applications, and we will be designing several modules based on that. So, if you see the screen, the name of this particular course is op amp practical applications, design, simulation and implementation. And to give you an idea what this course consists of, we will cover the data sheet of an op amp. So, if I give you a data sheet, then you should be able to understand what are the parameters written in the data sheet. So, we will see, we will understand the data sheet of an op amp, we will see a little bit of introduction just to brush up our knowledge, right, and then we will understand the hysteresis and need of hysteresis in switching circuits. Then a very important application of op amp is in ADC and DAC, analog to digital converter and digital to analog converter. So, we will see both applications of op amp, how can we design ADC, how we can design DAC based on op amps. In this particular course we will focus on a kit for professionals from TI, Texas Instrument, and this is called TI Analog System Lab Kit Pro, and using this kit we will design and build a function generator capable of generating square wave and triangular wave. We will also design and build a voltage control oscillator. We will also design and build automatic volume control using simulation. Further, we will understand how to build a constant current drive for measuring unknown resistance. We will take an example of a temperature control system and how can we build this kind of system using op amps as an on off controller and proportional controller. Then we will build a signal conditioning circuit for thermocouple to compensate for temperature correction. Finally, around week 12th we will see how to design and implement a speed controller of a DC motor using simulation and experiment, and we will also see how to build an op amp based ECG acquisition and BPM measurement. So, if you see really what we are covering, we are covering all the applications of MOSFET, applications of op amp, and of course when you talk about op amp you cannot leave MOSFET behind, you cannot leave transistor behind, right. So, this particular course will focus on the things that we have just seen right now, but to understand this whole session, understand everything about op amps and its application, we need to understand and we need to make sure that we have our basics clear, and that is why those who have not taken my earlier course on integrated circuits, MOSFETs, op amps and their applications, I suggest you to just go through it. So, to start this particular course, what we have to do is I will just take you around to kind of a journey where we studied the the basics of op amp, and then once we finish this, then we will move to actual application of op amp. So, when I talk about the journey, that means that what we have done in that whole course, those people who have not taken it, or those people even who have taken that course, it is good for them to refresh that particular course. So, this is a kind of summary of that course, and what I feel is that before we start applying the the theoretical knowledge into practical applications, let us just go through once again in case of a summary. All right. So, if you see we talked about integrated circuit, and integrated circuit is nothing but miniaturized low cost electronic circuit consisting of active and passive components, and it is built on substrate which is silicon. So, when you see a IC, when you open an IC, you will see a silicon chip within the integrated circuit. Then we talked about why integrated circuits, and we could easily see why. There are several reasons, including miniaturization, batch processing, better functional performance, mesh devices, increased operating speed, and significant reduction in the power consumption. Right. These are all the reasons enough reasons to make sure that we have to use IC instead of discrete components. And then we have also seen that ICs can be classified into several categories. ICs, when you look at the IC, it are metal can IC, that the ICs can be divided into few further categories: metal can IC, ceramic flat pack IC, 14 pin DIP, 8 pin DIP using plastic. Right. So, what kind of casing is there, based on that also the ICs are classified. Then if we talk about ICs in further, then they can be classified into two parts, one is LIC, one is DIC. So, what is LIC? LIC is nothing but linear integrated circuits, and in this LICs we are expecting that the relationship between the input and output of a circuit should be linear, while in case of DIC, the DICs are computers and logic circuits, and the circuit is either in on state or off state and not in between the two. Then we have seen monolithic integrated circuits, the circuits that are made on a single silicon chip, and the advantages is that it can be made identical, it is highly reliable, it can be manufactured in bulk, and it is low cost. And in fact, monolithic ICs are the best mode of manufacturing ICs. Then we have seen that what are the limitations, and the limitations are lower power rating, isolation between components with the integrated circuit is poor, components such as inductor cannot be fabricated. The passive components within the IC have small value, and if you require IC a passive component of higher values, then an external connection is required from the IC. Finally, the flexibility is not there in case of monolithic integrated circuit. That is why we have to opt for thick and thin film integrated circuits, and here the advantage is that the resistors and capacitors can be indicated, cannot be indicated, it can be used in high power applications, while some limitations are it cannot be indicated with diodes and transistors, while if you want to use diodes and transistor, it can be connected externally on its corresponding pins. Then what is the difference between thin and thick film technology? Thin film technology, using that we can deposit conducting semiconducting materials on a surface of a glass, ceramic base, or an oxidized silicon. For example, if you want to fabricate a resistor or fabricate a heater, then by controlling the thickness and width of the film, we can change the resistance of the heater. Additionally, different materials with different resistivity can be deposited. Same way, we can also fabricate a capacitor. In case of thick film technology, it is commonly called printed film circuits, where a screen printing or silk screen printing technique is used to obtain the desired circuit pattern. Now, the inks are used for printing circuit, that means the ink can be resistive, it can be dielectric or conductive properties, right, and the screens are generally made of stainless steel with wire mesh. We have seen this, right, and the example is of a greeting card or a marriage invitation card. You will see different form of figures, sketches, printings that is done using thin film, using thick film integrated circuit. Some advantages over the monolithic ICs are better tolerance, better isolation between components, flexibility in circuit design. These are the advantages. You see, when we were using monolithic integrated circuits, the flexibility was an issue. Here we can design the thin and thick film ICs on a flexible substrate. That is the advantage, because suppose let us say you want to develop a flexible sensor, example is a electronic skin, right. So, if you have a touch sensors, if you have a tactile sensors, if you have a force sensors and you want to wrap it on your skin, right, or you want to act those array of sensors, you want to use those array of sensors as a skin, electronic skin, then it should be flexible. This flexibility can be obtained using thick and thin film IC technology, while in case of monolithic it is not possible. So, these are the advantages of thin and thick film technology over monolithic ICs. Then we have seen hybrid or multi-chip integrated circuits, right, and what we have seen in this particular case, that the circuit is fabricated by interconnecting a number of individual chips, right, and here the diffuse transistor or diodes are the active components. It can be used for high power audio amplifier application, and finally, metallized pattern or wiring is used for interconnection between the individual chips. So, after we saw introduction of ICs, right, we also saw that the ICs can be fabricated on different substrates. We just discussed, right, flexible substrate. We can fabricate an IC on silicon, we can fabricate an IC on glass, we can fabricate an IC on plastic, right, or at least we can fabricate sensors on this kind of substrates, right. So, polymer we can deposit and we can fabricate. So, we can deposit, perform a lithography and fabricate a sensor on variety of substrates, alright. Thus, substrate is very important. Substrate is what? It is a base on which we are going to fabricate the whole circuit or whole sensor. So, it is a base. Now, in case of integrated circuits, particularly when we talk about op amps, right, or we talk about MOSFETs, then the substrate 95% is silicon, and then we have seen that how we can manufacture the silicon. So, for manufacturing of this silicon, what we have seen? We have seen that there are several processes. So, when we talk about manufacturing of silicon, production of electronic grade silicon, crystal growing, polishing of silicon and slicing of silicon wafers. We have seen that, we will again see in this coming slides. And when we talk about IC, right, when we open this case, like I said, we will find a chip, this is silicon chip, and within the silicon chip on your right side of the screen, top right, what you see is that there are lot of circuits integrated on this silicon chip, right, and the wire bonding is used to take the to bond the contacts from the silicon chip to the leads. Then we have also seen that there are several kind of silicon wafers. When I say several kind of silicon wafers, is based on size, right from 2-inch wafer to 18-inch wafer, right. Then there is a single side polished wafer and there is a double side polished wafer, right. So, we will see that we have seen silicon wafer processing. So, silicon when you talk about processing of silicon and in terms of wafer on wafer, then we have individual chips at the end of the fabrication process, and each chip is called a die, right. Each chip is called a die, and then we have also seen that there is a primary flat, and this primary flat is for a purpose. What is the purpose of a primary flat? To understand with respect to secondary flat if there is a presence of secondary flat or not, and if the secondary flat is present with respect to primary flat, where it is. Is it at 45 degree, is it at 90 degree, or is it at 180 degree, or the secondary flat is not present at all. Based on that, we can identify whether the wafer is N type or P type, or the orientation of the wafer 100 or 111, right. Then about the silicon, right. Silicon is manufactured in a clean room. What you can see on the right side is a bowl of silicon, right, and wafers are cut from this and polished to form the final wafers. Silicon is cut from this particular bowl to form final wafers, right. So, then we have also seen that for fabricating any sensor including MOSFETs, right, we need oxides. It can be gate oxide, it can be filled oxide, it can be masking oxide, and based on what kind of application of the oxide we are using, or based on the application, we can use different thickness of oxide. Generally, when it is gate oxide, it is around 10 nanometer, masking oxide 0.1 micron, while fill oxide is around 1 micrometer. And we all know that the silicon dioxide etchant is HF. So, the use of diffusion mask for common dopants, diffusion mask for common dopant is that it will save or it will not allow the dopant to enter through the diffusion mask, and this diffusion mask can be fabricated or can be designed using silicon dioxide, as you see on the figure. So, silicon dioxide over silicon substrate, right, this silicon dioxide here, right, this is grown on silicon and it is patterned, it is patterned on silicon such that the window is created in the center and silicon dioxide is protected on both the sides of this window. Thus, this silicon dioxide will act as a mask when we are doping the silicon, and this doping can be done either using ion implantation or diffusion, right, that we have seen, and the most common dopants are boron and phosphor. So, after this we move to op amps and silicon chip. When we see this silicon chip, right, this entire IC can be an operational amplifier, and like I said earlier, within the IC there is a silicon chip, and within the silicon chip there are billions of transistors, right. So, we have seen the brief history of the op amps right from 1946 right till 1965. A monolithic op amp was first designed and commercially available, right. Then Fairchild MUA 741 from 1967 till present we are using it, MUA 741, right. And then when we talk about op amp, generally we will see a 5 terminals. Actually this is op amp is a 8 terminal device, but most of the time we talk about 5 main terminals, positive and negative supply voltage, output terminal, inverting and non-inverting terminals, right. 1 and 5, pin 1 and 5 which you cannot see here is used for offset, while pin 8 is not connected, right. Then we have seen how the inverting and non-inverting inputs are used for, right. If you apply a signal at inverting, the output would be antiphase. If you apply the signal at non-inverting, the output will be in same polarity, same phase. Then we saw what are the advantages of op amps over transistor amplifier. So, there are several advantages that are listed over here, right, which are less power consumption, it costs less, it can be manufactured in bulk, more reliable, easy operation, easy design, right. So, these are the advantages of operational amplifier over transistor amplifier. That is why this course is designed to use the op amp and use this op amp for several applications, right, not transistor based amplifier for several applications. So, you should understand that why we are using op amp, right, and in fact some of the applications of op amp are right now listed in front of you: audio amplifier, signal generator, signal filters, biomedical instrumentation and numerous other applications, right. So, op amps are used in signal conditioning circuits, they are used in amplifiers, they are used as differentiators. We have seen in the last class, last course particularly, we have seen op amp as an integrator, right. We have seen op amp as a adder, then we have seen the functionality of a op amp as an application for different circuits, right. And then we have also seen how we can design several circuits, not only design, but also simulate those circuits using Simulink. So, Simulink, then breadboard. Here we will do something different, alright. We will now use a TI kit and we will see how we can implement several application of op amps or op amps in several applications and try to understand how it operates or how it works. So, then we have seen ideal op amp, and ideal op amp has few characteristics such as infinite voltage gain, infinite input impedance, 0 output impedance, infinitely fast. Of course, op amp has two golden rules, we have discussed those golden rules. First is that the input to the op amp draws no current, and second is the output will do whatever it can to make the voltage difference between two inputs 0. These are the two golden rules. We have seen the ideal versus real op amp, right. Real is nothing but actual or practical op amps, and we see that there is a difference in terms of the character parameters, where we say voltage gain is infinite, actually it is about 10⁵ to 10⁹. When we talk about gain bandwidth product is infinite, it is about 1 to 20 megahertz. Input resistance infinite, in actual case it is 10⁶ to 10⁻12 ohms, while output resistance is 0, in actual or real case it is about 100 to 1000 ohms. Then we have seen balanced unbalanced power supplies, right, and we have seen single ended output and double ended output. I will just skip this fast, just to make sure that the balanced and unbalanced power supplies are used in several applications. Most of the application you will see balanced power supply, while some applications also used unbalanced power supply. Same way single ended output is with respect to ground, double ended output it is not with respect to ground, that is why it is also called floating output. Then we move further and we see that the internal op amp formula is nothing but V out equals to gain into V plus minus V minus, is inverting minus non-inverting or non-inverting minus inverting. Whatever is great, like whatever is higher, the signal at inverting is higher, right, compared to non-inverting, then our output will be negative. If the signal at non-inverting terminal is higher compared to inverting, our output will be positive, right. Then we have seen feedback, negative feedback, and negative feedback is used for amplifiers, while positive feedback is used for oscillators, right. So, we have seen that what are negative feedbacks, what are positive feedback, right. Then we have seen the internal stages of operational amplifier. It consists of differential amplifier, intermediate state, level shifter state, output stage, and most of the op amps are now replaced by MOSFETs. The internal circuit that you see here BJT, most of the cases now we are using MOSFETs, alright. Then these are very important parameters or characteristics of the operational amplifier, starting with open loop gain, right. What is open loop gain? It is a voltage gain of operational amplifier when no feedback is applied. So, practically it should be or it is several thousands. Second is input impedance. It is finite and typically greater than 1 mega ohm, but for FETs for the input stage it can be increased to several 100 mega ohms. Output impedance around 1 to 2 ohm. Bandwidth of practical op amp in open loop is very small, but by using negative feedback we can increase the bandwidth to desired value. Input offset voltage. When both input terminals are grounded, the output should be 0, but when you do that, like I said in the last course, that when you ground both the input terminals of the operational amplifier, you will not find that output voltage is 0, right. And to make that output voltage 0, a small voltage is required to apply to one of the input terminals, and that small voltage is nothing but your DC offset voltage, is called input offset voltage. Same way, if you talk about input bias current, what is input bias current? If you come back on the screen, for ideal operational amplifier, no current flows into the input terminals, right. So, but for practical op amps, you will see that the input currents are very small, around 10 raised to minus 6 to 10 raised to minus 14 ampere, right. So, the input terminals, which are the base terminals of two transistors, do not current small DC current. This small base current of transistors are nothing but the bias currents denoted by IB1 and IB2. You see why this happens? Because the two transistors of the differential amplifier. So, when we see most of the op amps are used as a differential amplifier, right, differential amplifier for the input voltage. The two transistors of the differential amplifier must be biased correctly, but practically it is impossible or it is not possible to get exact matching of two transistors, right. This mismatch of the two transistors will allow a small base current to flow or small DC current to flow to the input of the transistor, right. This small base currents of the transistors are nothing but input bias currents, right, bias currents denoted by IB1 and IB2. So, how input bias current is measured? The input bias current is measured by using this formula, where IB equals to mode of IB1 plus mode of IB2 by 2. Where you talk about input offset current, it is the difference in the magnitudes of input bias currents, right. IB1 and IB2 is called input offset current and is denoted by IOS equals to mode of IB1 minus IB2. Right. One very important point that you have to remember here is that both input bias and offset current depends on the temperature. If you change the temperature, you will find that the input bias and offset current also changes. Zero input current, right. What is that? The current drawn by either of the input terminals is 0, right. In reality, the current drawn by the input terminal is very small, of order of micro ampere or nano ampere. Hence, assumption of 0 current is realistic. These are all realistic simplifying assumptions, right. So, actually ideally what will happen, that the current drawn by input terminal should be 0, but practically when we measure it, it is about micro ampere to nano ampere, which is close to 0. Hence, 0 assumption is realistic. Second is virtual ground, very important in case of operational amplifier. So, this means the differential voltage Vd between the non inverting and inverting terminals is essentially 0, correct, essentially 0. This is obvious because even if the input voltage is few volts, due to large open loop gain of the operational amplifier, the difference voltage at the input terminal is almost 0. We have seen that, right. So, let us move forward. We have seen the concept of virtual ground, right. So, even if one of the terminal is grounded, the second terminal is also considered as a ground, and that is a concept of virtual ground. Then we have seen differential mode gain. Differential mode gain is nothing but VO or output voltage equals to differential gain into difference of input voltages V1 minus V2, right. So, AD is nothing but gain with which differential amplifiers amplifies the difference between two input signals. Hence, it is also called differential gain, because it amplifies the difference between two input signals, right. Common mode gain, what does common mode gain means? So, it is a factor by which common mode input voltage is amplified by operational amplifier. So, what exactly common mode gain means? If we apply two input voltage which are equal in all respect to differential amplifier, right, that means let us say the voltage at the inverting terminal we consider V1, voltage at non-inverting terminal of the op amp we consider V2, and if V1 equals to V2, then ideally what should be the output? Output voltage should be VO equals to differential gain into V1 minus V2, V1 is equal to V2. So, output voltage should be 0, output voltage should be 0, but in practical op amps, practical differential amplifier, right, it does not only depends on difference voltage, but also depends on the average common level of two inputs, and such an average level of two input signal is called common mode signal, denoted by Vc or VCM, and this VCM can be found by formula VCM equals to V1 plus V2 by 2. Right. Thus, we cannot just say that VO equals to AD into V1 minus V2, but the output voltage of the operational amplifier depends on AD V1 minus V2 or AD into VD. V1 minus V2 is what? VD, right, differential voltage. So, AD into VD plus ACM into VCM, right. So, the output voltage depends not only on the differential mode gain, but also on common mode gain and common mode voltage as well as differential mode voltage. So, then we have seen common mode rejection ratio. So, what exactly common mode rejection ratio means? Right. Common mode rejection ratio is the ratio of differential gain to common mode gain. Ideally, the common mode voltage gain is 0, right, because we do not want common mode gain, we want only differential gain. But so, ideally in ideal situation, if we say that common mode gain is 0, then what will be CMRR? CMRR would be AD by 0, which will be equal to infinite, right. The CMRR ideally should be infinite, but practically you will see that AD is large and ACM is small, hence CMRR is also very large. And many times you will also see that CMRR is expressed in decibels. Now, input offset voltage we already discussed, right, input offset current, right, the algebraic difference. What is the technique to null the output voltage? Technique to null the output voltage. You see, when we short the input terminals 2 and 3 to ground, right, practically it should be 0, output voltage should be 0, right. So, but it is not 0. So, we have to make it 0, that is called nulling output voltage. So, we have to connect a potentiometer between compensation pins, right, 1 and 5. I told you earlier 1 and 5 are the compensation pins, right, and with a wiper to VEE. So, potentiometer, with the help of potentiometer we can adjust the output voltage VO to be 0, right. So, we turn the potentiometer such that we apply a small amount of voltage which is called offset voltage to make our output voltage 0 or to nullify the output voltage. Now, we then found that the input bias currents affect the amplifier operation, right, and we took an example of how the input bias currents IB1 and IB2 affect the operation, all right. So, we will just skip this, you can just look at my earlier course, right, and look how exactly the input bias currents IB1 and IB2 affects the operational amplifier or amplifier operation. Then we also saw how we can compensate the effect due to the bias currents, right, and what resistance can be used to compensate the effect of bias current, right. So, again you see the videos that are already available, and when you see that you see those videos, you will understand how we can compensate, or how we can exactly compensate the effect of the bias currents. Then if you come back to the screen, what we see, another question is, how does input offset voltage, or how does input offset voltage affect the amplifier operation, right. Earlier it was input bias current, here it is input offset voltage, right. So, this also we have seen. So, just look at the videos please, right. Then the next example is thermal drift, right. These are all data sheet parameters, by the way, these are all data sheet parameters, right, data sheet parameters. So, when you see input offset current, input bias current, input offset voltage, CMRR, these are all data sheet parameters. Okay. So, just look at it, thermal drift, right. Being semiconductor devices, op amps are subject to a slight changes in behavior with change in operation of the temperature, or with change in operating temperature. So, if the temperature changes, because it is semiconductors, right, the op amps are subject to slight changes. What behavior changes are there? A circuit nulled at 25 degree may not remain so when temperature is rises to 35 degree. So, if there is a temperature difference of 10 degree, then you will see there is a drift, and this is called, of course, this is called a drift, and bias current, offset current and offset voltage change with temperature, right. So, thermal drift is very important parameter, we need to understand. Thermal drift parameters can be specified for bias currents, offset voltage. The manufacturer data sheet specifies the quantity of any particular op amp. It tells about the amount of input offset changes with each degree Celsius change in temperature. So, for example, if you take LM741A, the worst case drift is 15 microvolts per degree centigrade. So, if the circuit has to operate from 0 to 60 degree, the input offset voltage, right, or input offset could change by 15 microvolts per degree centigrade into 60 degree, which is 0.9 millivolts over 60 degree temperature change, which is really huge change, right, 0.9 millivolts. So, let us take an example and let us see, a non-inverting amplifier with a gain of 100 is null at 25 degree. Okay. What will happen to output voltage if the temperature rises to 50 degree centigrade? So, from 25 we go to 50 degree centigrade, and for an offset voltage drift of 0.15 millivolts per degree centigrade, right. So, in this case it is very simple, we can write the input offset voltage due to temperature rise is nothing but 0.15 millivolts per degree centigrade, right, into 50 minus 25 25 is equal to 3.75 millivolts. Since this is an input change, the output voltage will change by VO equals to VOS into ACL, or 3.75 into 100, gain of 100, right, 375 millivolts, right, 375 millivolts. This is a huge change or major shift in the output voltage. Thus, it is very important to understand the thermal drift, and based on the thermal drift, based at different temperature, you have to nullify your op amp, or you should understand the temperature compensation circuits. So, other parameters, input resistance, input voltage range, large signal voltage gain, output voltage swing, right. These are the parameters you will see in the data sheet. So, impedance in looking into input pins, LM741 has a minimum input impedance of 2 mega ohms. Many op amps have input impedance of or over 1 giga ohms, alright. Input voltage range, how high or low voltage at the input pins can be applied before op amp does not function properly. Practically we know that if there is plus minus 15 volts supplies, the input should stay below plus minus 13 volt. Large signal voltage gain, what is that? The gain of op amp at DC, that is low frequency, right. Earlier we stated that the gain was infinite, we always see that the gain is infinite, right, but in real situation it is large but not infinite. The typical gain is about 200 volts per millivolt or 200,000, right. Many op amps have gain of greater than 10 raised to 6. Output voltage swing, what is that? The output can swing all the way to power rails, right. It cannot go all the way to plus minus 15, but the maximum output voltage also depends on the load current. With a smaller load, the output can go higher than with a larger load. It is obvious, right. Most op amps can swing to the output to within a few volts of power rails, right. These are the special op amps called rail to rail op amps that can swing the output to within 100 millivolts of the supply rails. It goes as close as to 100 millivolts of the supply rails. So, if it is plus minus 15 volts, it can go 14.9 volts, alright. So, these special op amps use battery products which power supply may be 6 volts or less. So, we have to see how much voltage we are applying. Then there is a output short circuit current. What is that? How much current the output can source or sink from the output pin is the output short circuit current, right. The output voltage will drop near 0 volts when delivering the maximum current. Typically, the op amp cannot deliver more than 25 milliampere. Then we have seen common mode rejection ratio. There is another parameter in the data sheet. What is this parameter? The ratio of the difference gain to the common mode gain. We have seen that, right. AD by ACM, and CMRR should be extremely high. CMRR should be extremely high. So, if you talk about 741, that is LM 741, the worst case scenario for CMRR in LM 741 is 7 dB, while and typically about 90 dB, right. Some instrumentation and differential amplifier can have a CMRR over 110 dB, that is about 300,000, very high CMRR, excellent for the operation amplifier to be used as an amplifying circuit. Power supply voltage rejection ratio, PSRR, this is another parameter. Then when you open a data sheet, you will see PSRR. So, what is that? This tells about how well the op amp filters out the noise coming from the power pins, right. So, noise can be generated from the power pins, how well it can be filtered out. So, using a 12 volt supply with 100 millivolts of ripple of at 120 hertz, how will this affect the op amp circuit? Let us take an example where we are using a 12 volt supply, right, and there is a 100 millivolt of ripple at 120 hertz. In this case, with a PSRR of 96 dB, the ripple seen by the input will reduced by a factor of 63,000. So, with a 100 millivolt ripple and PSRR of 96 dB, the op amp inputs would see a ripple of 1.6 microvolt. For a gain of 100, the output will have a ripple of 160 microvolts. Even when there is no input of the op amp, this is why it is required to filter the power supply and to have a good PSRR. You understand? See, if we have this example where 12 volt power supply is there and about 100 millivolt of ripple is there at 120 hertz, right, then with a PSRR of 96 dB, right, PSRR of 96 dB, if we consider the output would see about 160 microvolt of ripple voltage, and that is not good, right. That is why we should use a filter, right, for the power supply, right, to have a good PSRR. Now, transient response, what exactly transient response means? This gives you an idea of how fast the op amp will respond to pulse input, right. So, rise time may be the time it takes from signal from 10% to 9%, how fast the op amp is, transient response. Then we talked about slew rate. What is slew rate? Slew rate is how fast the output can change, right. When you apply input signal, how fast the output can change with respect to input signal. This gives you an idea of the maximum frequency and amplitude signal that op amp can handle without any distortion, right. And then we have taken an example, and from the example what we found is that to operate without distortion, the way is to lower the voltage or lower the frequency, right. So, how does that work? How does that work? Either we can lower the voltage or we can lower the frequency. So, let us say Let us see this example. Let us the LM741 output typically can only slew at 0.5 volt per microseconds. If you have performed the experiment slew rate experiments, you will know that it is around 0.5 volt per microsecond. Now, if you have 10 kilohertz 10 volt peak sine wave on the output, the fastest point at which the voltage changes is at 0 crossing. The rate of change is dV by dt. So, 10 sine 2 pi into 10,000, right. 10,000 is a kilohertz. So, 10,000 T equals to 0.63 volts per microsecond. Since 0.63 volts per microsecond is above 0.5, there is a good chance that the 10 volt peak 10 kilohertz sine wave will have a distortion at 0 crossing, right. So, if you want to avoid this distortion, what we can do? We can either lower the voltage so that it comes around 0.5 volt per microsecond or below it, or we can lower the frequency, right. By lowering the voltage or frequency, we will see that the rate of change dV by dt would be less than 0.5 volt per microsecond, right. So, again LM47 is considered as a slow op amp. However, you can get op amps with a slew rate in excess of 1000 volt per microsecond or 1 volt per nanosecond. So fast, right, slew rate can be very fast. Okay. Then we move to next parameter, and this parameter is also mentioned in the data sheet, that is called bandwidth or gain bandwidth product. The gain is as a function of frequency for a smaller signals. This means that with a 1 megahertz input, the maximum gain is 1. Actually, the gain is less than 1 because gain bandwidth product is defined as 3 dB point, right. We have seen why 3 dB, where the voltage drops around 0.707 of its original value. If the signal input signal was 100 kilohertz, the maximum gain would be 10. With a 10 kilohertz input, the maximum gain would be 100 and so on, right. So, this is how the gain bandwidth product is defined, and the LM741 is considered again as a slow op amp, right. There are op amps available with a gain bandwidth product of or gain bandwidth product around and over 1 gigahertz. So, what is another parameter? Supply current, the current drawn from the power supply when no load on the op amp, right. So, there are low power op amps available that runs on the less than 10 microampere. Usually the faster op amp, the power it requires is more. The faster op amp more power, slower op amp less power. Okay. So, this is all about your data sheet of the op amp. So, in this particular module what we have seen? We have seen that we have just quickly summarized about ICs, we have quickly summarized about the substrate, and we have seen characteristics of op amp as well as some realistic parameters and some characteristics or parameters that are listed in data sheet, right. In the next module we will see some applications of op amp, and then we will move to actually implementing the circuits, right, using not only simulation, but like I said and I mentioned, we will use kits to perform the experiment, all right. So, just go through this particular module and understand and make your concepts clear, because these concepts would be used in the following classes, right. Till then, take care.